All right, third try for the third problem, which is the last problem for the module. Unfortunately, this is the fifth or fourth lecture in the module. So I'm going to look at this sphere. Say it has a 10 centimeter radius, and it's charged to 10 microcoulombs. Okay. And I want to see what the potential is right here. What's the potential at that surface, at this, at the radius from the distance here. And that's going to be, as long as this is a spherically symmetric charge distribution, V equals KEQ over R. Now, like I said, this is the same for any spherically symmetric charge distribution, which means that if I take a cut here, or I take a cut here, or I take a cut here, as long as I take one of these radial cuts, there's no difference in what the local environment looks like. Basically, I can't tell from the charge distribution which orientation this has. So, if I labeled this point A, and I was just measuring the charge distribution, there'd be no way that I could tell which way A was pointing. It could be pointing over here, over here, over here. And so as long as that's true, we have this outside of our sphere. Now if I were to cut it and sort of measure what the voltage was, or the potential was, on the inside of the sphere, then I could tell what was going on. So for example, if I were to measure the potential here on the inside of a uniformly charged surface, then on the inside the potential is constant, and the drop-off is just this 1 over r dependence over here. But if this were uniformly charged over the volume, so that the charge density here and the charge density here and the charge density here, all of these little dots have the same charge density, well, in that case, outside it looks exactly the same, comes here to VR, but if you go down closer and closer to 0, you have this linear increase until you come here. So these are two different charge distributions, technically, but outside of the sphere, they're completely identical, which means that you can always use for a sphere, this is your potential. All right, and so what I'd like to do is I'd just like to use this to calculate the potential right at the edge there. Okay, so how do I do that? Well, what I'm looking for is V at 10 centimeters, right? So when I use this equation, that R isn't the distance from the sphere, it's the distance from the center of the sphere, right? Which happens to be the radius of the sphere, which is 10 centimeters. KE, that's 9 times 10 to the 9th newtons meters squared per coulomb squared. Q, I just said was 10 microcoulombs. R, I said was 10 centimeters, so 0.1 meters. All right, so that's 9 times 10 times 0.1, so that's 9 times 10 to the 9th. The micro gives us a -6, and the 0.1 gives us another +1. Okay, so that gives us, oh, and I have another 10 from this. This is another 10, so that's 9 minus 6, so that's 3 plus 1 plus 1 is equal to 5. So that's equal to, okay, well, actually I should cancel some of these things out here. Newton meters per coulomb. A Newton meter per coulomb is a volt. So we have 900 times 10 to the 3 volts, which is 900 kilovolts. And that's what I got over here. So because right at this border and everywhere beyond the border, this is the same, this formula is always applicable for a spherically symmetric charge, we are able to use that. So this is good for a point charge because a point charge is spherically symmetric. It's good for a small sphere. It's good for a big sphere. It's good for an even bigger sphere. That's all we need to do with this sphere. Right? And that's it for this unit. Okay? Next unit, we'll do circuits. Do some practical stuff with it. Bye now.